In this example, we will be sampling a continuous sinusoid. Shown in green is a portion of it, 1 second, with a frequency of 5 Hz. As we collect samples, we will be indexing them with the notation n. We start at n equals to 0 as it makes sense to believe that the signals that we're collecting from an instrument starts when we, let's say, push a button at exactly time equals to 0. This will cause some consequences as we will see later, but that's one of the reasons why we usually start at n equals to 0. We continue collecting these samples at the separation equals to the sampling period, that in this particular example is 1/60. So we get all those red dots, which are just samples from the continuous signal in green. So the exact time for the index 1 is equal to Ts. And for example, for the exact time where the time index 3 is, it's just 3 times Ts, and so on. So if you wonder how many samples we collected for this waveform, you can solve for capital N, substitute T by 1 second and Ts by 1/60 and believe that the total samples you collected is 60, but keep in mind the index at 0, that will add one more. So the total number of samples here, the red dots, are equal to 61. Mathematically, to go from x of t to x of n, what we need to do is to substitute t by n ts. Notice that the convention is to describe x of n. That does not require us to write x of n ts. Now let's substitute ts by 1/fs. Following the Nyquist theorem, fs should be greater or equal to 2 times f, the maximum frequency of the sinusoid. Therefore, the maximum frequency, normalized frequency in the discrete time, can only be 0.5. So for expressions like this, where the normalized frequency is 0.35, we know that everything is okay. On the contrary, for expressions like this, where the normalized frequency is 0.8, there must be something wrong in there. In the discrete world then, Fn is bounded between -0.5 and 0.5 normalized hertz. In the plot below, the red arrow indicates the normalized frequency corresponding to a sinusoid in the continuous world of 5 Hz. Notice that the normalized frequency is simply f divided by capital Fs, which in this case is 0.0833. Keeping the sampling frequency at 60 Hz but increasing the continuous waveform frequency to 15 Hz, this is what we obtain for normalized frequency and the position of the red arrow. If we increase the continuous frequencies to 55 Hz, we can see that the normalized frequency goes outside our limits between -0.5 to 0.5. So we have an expression with normalized frequency equals to 0.9167, and we know that there must be something wrong as we have violated the Nyquist rate. We can actually see in the red waveform that the frequency is actually lower, much lower than 55 Hz. So we will inspect what's going on here and hopefully calculate the value of this lower frequency. What we say for these cases is that aliasing occurs when a continuous signal is sampled at a rate that is insufficient to capture the changes in the signal accurately. This can cause different signals to become indistinguishable or aliased when sampled. Essentially, the signal appears to be of a different frequency than it actually is. This lower frequency depicted in the red waveform is called apparent frequency. Extending the frequency axis, we can see that the location of this normalized frequency will generate the apparent frequency, which value is indicated by the gap distance, calculated by 1 minus 0.9167. In the continuous world, the red waveform will have a frequency of this normalized frequency times Fs, giving us 5 Hz, the lower frequency. Another way to visualize where the apparent frequency will be is to think of the frequency rolling over at the edge of 0.5, coming back from -0.5, completing a distance of d plus d1, which should be equal to 0.9167.